So this was work that I did with Ben, was the other main researcher, and supported by a few of the members on the WATonomous team. And it's a project that we're actively pursuing to integrate with the vehicle platform and deploy it to testing on the private track over the summer. So starting off, so for the outline, I'll definitely motivate the project. I'll talk about the baseline and data set that we're using. I'll probably skip the literature survey and then just talk about our approach and the initial results that we saw. So perception, okay, so the overall goal here is we want to use this very high resolution sensor data and then transform that into commands that we send the vehicle, right? Like we take in images of people around the vehicle, and then we want to send a steering command to the vehicle to avoid them. We want to have some sort of understanding of what the pedestrians are doing, but what really constitutes a understanding. So a lot of the research community isn't focused on big questions like this. They're more focused on very specific tasks. Like understanding could be pointing to a certain place in the image and saying that's a pedestrian there. Or maybe like this is the orientation of the pedestrian in the image. So we're seeing over time in the research community these specific tasks that are being challenged to the research community are heading towards a deeper understanding of the road scene over time. And the data set that we focused on is one of the forebearers in that sense. So action classification is one of these tasks that we feel like is pushing the research forward to a deeper understanding. It requires relating spatial and temporal information across frames, for example. And the data set we're using to experiment with this task is the road data set. So the road data set actually can be used for 3 different tasks. The first one is what's been studied well over the past decade, which is detection, tracking, and categorical classification. So I think we're all familiar with that. Task 2, this is the novel task that the dataset introduces, which is categorical action classification. So basically just the labels, they have additional labels that aren't just the type of the active agent in the scene, but also the action that they're going to be carrying out. So the vehicle in front of us here is stopped. There are pedestrians that are crossing from the left or the right of the road, stuff like that. And then there's also this third task that I'm going to ignore in this presentation. So we'll be focusing on task 2 here. So along with this data set that has these ground truth labels for what we want our algorithm to be able to produce, they released a neural network architecture that produces metrics that we use as a baseline for our experimentation. Again, I'm not going to talk about the model architectures in this tech talk. But yeah, just know that there's this baseline that uses a certain model and achieves certain metrics. We want to take inspiration from this model and improve on it. That's kind of the main like research motivation. Then there's also practical motivations of deploying this to our vehicle as well. So yeah, I'll skip the details of the background literature review, but basically the action classification problem is pretty well studied in not the road scene domain, which the RADNET dataset focuses on, but in human action domains. There's existing large-scale data sets, yeah, that you can read about in this link. Let's see. Okay, I guess the one thing I will say about the literature review is that most of the algorithms that are in the literature focus on action classification using views. So this means you don't give the algorithm every single frame in the video and say, give me every single action that happened during this video and exactly where it was. The network would have to have a very large memory footprint to do that. So kind of a hand engineering step that is done is feeding in a temporal crop of the video. So maybe just 15 or 30 frames of the video, and asking the network to produce action classes based on just that temporal crop, which we'll be referring to as a view. There is other research that I can refer you to that is doing longer, like in entire video-based architectures. But yeah, those aren't really giving competitive results. And then we also did a literature review on existing detection and multi-object tracking in the image domain. And this work is pretty similar to what's going on in the perception division currently. Okay, so yeah, I guess I'll make reference to the baseline just to compare what we did differently. So we coined our approach the RADNET, the Road Action Detection Network, and it's a two-stage. So it separates the detection and action classification tasks, which is unlike the baseline. So in the baseline, they produce the bounding boxes for the active agents and their actions within a single pass through the network. But our kind of thinking was, well, we already have very good architectures for detecting active agents. Why would we kind of start from scratch re-engineering those when we could just have a two-stage approach? So the first stage can use any active agent detection and tracking algorithm, of which there exist many. And this produces bounding boxes for detected agents in a single frame. The second stage is action classification. So this is focusing on task 2 from the dataset. And we experimented with a few different model architectures that came out of the human action classification domain. And the main hypothesis we wanted to test before I get into the results is, do these architectures that were developed and currently only tested on human action domains, do they work well for road scene domains? And then also, can we kind of share the representations of actions between these different domains? So if you see, like, is there some atomic building blocks of actions in a video? Like, can you teach a network to recognize the motion of like turning left away from the ego perspective and humans in YouTube videos turn left away from the ego perspective, and also cars turn left away from the ego perspective in the road data set. So can you learn, do these kind of, can the network learn these atomic actions, these representations of actions, and transfer that between domains? But before I get to those results, here's what the overall classification pipeline looks like, if just at a schematic form. So the first stage is the agent detector and tracker. So to do this, let's say we want to detect and classify actions in a keyframe, which we'll say is the middle of some view, which comes from the overall video sequence. So we take that keyframe, which is usually selected as the middle frame, we pass it through the agent detector, which produces the box prior, and then those box priors, along with the context, that view around the keyframe, are passed into the action classifier, which then produces these dual classifications that contain the agent as well as the action classes. So yeah, I think it's pretty intuitive. Yeah, so I think I already talked about this, kind of a hypothesis for using the detection and tracking algorithms. Like, we know there are many existing good algorithms that perform well on other data sets, such as the KITTI benchmarks, and so we know they'll perform well on road as well. Or we were pretty confident in it, and yes, they did perform well. So this hypothesis we were a little bit less sure of, and it's the main one that we reported on in the write-up. And I already talked about this earlier. So okay, so to test these hypotheses, we experimented with a feature extractor catered towards videos. So this was the backbone that extracted, if you're familiar with vision architectures, it extracts these high dimensional feature vectors from the video. And then there are a few different heads that you can apply to produce classifications from these high dimensional spaces. You can use a feed forward head that just reduces the dimensionality back to your smaller classification space, or you can use a more complicated relational based head called actor context actor relation head. And yeah, the details will be in the literature review. Actually, there's a whole nother presentation on the literature review that'll have more detail, so I can forward you that as well. But yeah, so we're just basically using these things, and then on top of these two heads, we wanted to experiment with two different weight initializations. Of course, the algorithm that we're developing is represented by the convergence of these weights to certain values once we like back propagate enough examples through the parameters. So how do you initialize these, I think, millions of parameters? So do we initialize them with these hypothesized atomic action representations learned from a human action data set, or do we initialize them randomly? two different options. And if there is value to transferring these atomic action representations, then we expect that the initialization using the weights from a network trained on these human data sets would yield a faster convergence than random initialization. So this kind of lays out those two different designs that we were testing. So one, there's two settings for the weight initialization. There's random weights, and then there's initializing with weights that were trained from a human data set. So these two settings test for test the hypothesis of if action representations are transferable. And then these are passed through the slow fast feature extractor, which is always part of the model. But then the second difference is we experimented with different feed forward head, which doesn't add any additional inductive bases, kind of. And then there's the actor context, actor relational head, which tries to enforce some more relational biases on the features. These both just produce class scores for each of the action classes. And then we use our annotated actions to produce a loss, pass that into the optimizer, which then takes care of updating the parameters of this network. Yeah, okay. So in the last 2 minutes here, I'll just show the results. But basically, they were promising. It's why we're continuing on with this research. So first, discussing. Okay, well, let's just look at this graph here. Using the pre-trained. Okay, actually, I'll just go with what my bullet points say here. So if we just look at the green and orange, the only difference here is the which network head was used. So the green is using the more sophisticated actor context actor relational head, which yielded a few points of performance. Can't really be said if this is just because of the increasing number of parameters of the network, or if the actual design, like the operations that are being conducted, yielded this boost. It's kind of a common question when you try to make a model more complex. Is it just doing better because it's more complex, or did the complexity you added actually make it better in some way? Anyways, but the bigger difference we saw was pre-training on the human data set profoundly improved performance. Like immediately, just when we started training, basically within the first run through the data set, we'd already basically converged at the final performance of the classifying like actions in road scenes. So if you see here, like at the very beginning of the graph, like this is our performance after doing one epoch or one run through the data set. We'd already come very close to our final top performance. So yeah, basically there was a lot of knowledge that was able to be transferred between the human action domain and the road domain, so much so that there wasn't much more to be learned, basically, about actions in the road domain. And then the other observation is overall, even when we fully converged from the random initialization to the best we could do by only using the data in the road dataset, we still see that there's this big, almost 10-point difference between the performance we could achieve by only learning from actions we saw on the road versus learning from actions that we saw in like YouTube videos as well. So evidence for a shared action representation space between different domains. Okay, so yeah, I think that was the main point. I'll just let this video play of what our algorithm actually looks like on the video dataset. And I'll leave it off with what we're trying to do now is publish the findings in a computer vision conference after we do a little bit of refinements and a little bit more experimentation. And then over next summer, we want to deploy this to the actual vehicle and integrate it with our environment modeling software so that we can understand the of course, have this information affect our control decisions of when to overtake a vehicle, when to stop for a pedestrian, things like that. Okay, yeah, let's do 5 minutes for questions.
Seems like there's no questions.
Rowan, I have a quick question.
Oh.
Yeah.
I'm pretty curious about what the inference performance was like.
So using just isolating the action classifier with the ACAR head, we're able to get around 35% mean average precision across all of the classes. And the reason why it's like low is because there's this long tail. So as we get down to these very infrequent action classes, we see that we basically never classify it correctly. And then what we do is we take the mean of all of these accuracies across all of the classes. So yeah, basically, I think the question is better answered by looking at a histogram of the different classes like this. And one of the refinements we're currently working on is there are common approaches to, I mean, like the problem overall is that identifying these low frequency classes are hard, but you can basically bias the network to respond with these classes more often. So it boosts your like score that you report on the report. But anyways, to more like systematically identify these categories better, we would just need more data. So yeah.
Thanks. So my question was actually about when I say performance, I actually mean inference speed. So like, what were the hardware you guys used, and if it's actually something that's obtainable on our vehicle platform?
Yeah. So that's another thing we need to do in the report is actually do our profiling. I basically have no idea. Yeah.
The reason why I'm asking that is because, okay, so you guys were using ACAR, which is probably not the same thing as just reducing the dimensionality all the way from input to like the number of classes you have. Because what my experience with SlowFast has been that it takes a clip of video as input, and I saw that on the output video that our prediction result was actually really smooth. Like we basically have like one one different bounding box and it's, I guess, slightly different classification for every frame. And I was thinking that's like a massive amount of data we're putting into the neural network, right? Like, does that mean for every frame, we're simply just like dequeuing the outdated frame and then enqueuing only one additional frame to the input, or like, well, how do we do the inference here?
No, so you need to recompute the feature vectors across the entire view. So it's not just like queuing another frame, and you only take the penalty for that additional frame, because the features that you extract using slow fast are calculated based on the entire temporal range. They're not like segmented down. So you're doing your convolutions across, like, strided across the entire temporal dimension. So if you introduce one more frame, the output of those convolutions could be totally different.
That's what I was wondering. Wait, so you guys are, yeah, how did you like continuously update your, how do you continuously update your input? So do you do some feature extraction on just one frame and concatenate in
No,
some?
updating, you're just giving it. So you can think of one frame in the action classifier as one view, as one temporal crop around a keyframe. So what we're visualizing here is the keyframes, but these aren't the inputs to the model. The input to the model are the views. So we're only visualizing one specific frame within that view.
Interesting. Oh, so this is your keyframe, meaning that your input sequences are kind of like your views, but say shifted next in time by like one frame at a time. Is that how this is being done?
Yeah. So yeah,
Oh,
we take a view, we get this output for the keyframe, then we shift one keyframe down. We have like that view that corresponds to that keyframe, and then we just keep on doing that.
I see. Yeah, Rowan, that's what I was asking by like dequeuing the outdated frame and updating one frame. It's just, yeah, sliding that view down in the temporal dimension. And okay, so this gets back to my initial question about the compute cost, because I know, yeah, if we're only updating the view by shifting to the down in time by one frame at a time, that's quite a lot of computation. That's why I was curious.
Yeah, no, that's what'll make the project of deploying to the vehicle fun.
Right? Okay, I see. Huh, yeah, this is definitely one way to do real-time inferencing. So I guess when we do real-time, we'll have to keep our keyframe at the end, I guess, right?
Yeah, the design of real-time, there are definitely a few different options, and we'll have to see how they pan out, like the performance in the real world.
I see.
Yeah. Like,
Yeah.
it's some actions, it's hard to say what the person is doing without seeing what they like. In our human brains, it feels real time, but we never really know what the person is doing immediately when we see them. We know what they're doing maybe a second ago.
Okay, that makes sense. But the reason why I'm asking that because my previous approach to quote unquote real time was having like an acceptable delay of, I think it was around 1 or 2 seconds. Yeah, for my particular application, it was not critical. But for us, I can see that we should do some research on like what the best option is for real-time inferencing, because I don't think we want to be deciphering the actions of our subjects by later than say a second, right? That can be dangerous.
I mean, it's your accuracy versus real-time trade-off there. You want to be real-time but not be able to do it well? Or do you want to be able to do it well but have a delay? Yeah.
Yeah, because I understand the keyframe impacts your results because you only run your detection on that keyframe, right? You don't do it through the for every frame in your input.
So that's another change that we want to make, is we want to be able to do it for every frame, like do detection on every frame, and only do that once, because that's like a static thing. And then that will be able to do action classification better, because we can track the agent and their exact features from the slow fast feature extractor across the entire view, instead of just like assuming that they stay still and taking the same features from their position in the keyframe across the entire view.
Exactly. When it's static, you have to make that assumption. So are you saying you guys are trying to make it not static?
We're trying to make our architecture support or perform better at highly dynamic positions across the view.
Oh, I see. Okay, so this is another variable in your research, right? That's pretty exciting.
Yep.
Nice.